I've spent more than 2 decades in the trenches of automotive engineering, and today I want to pull back the curtain. I'm going to walk you through the actual blueprint we use to take a micro-electric vehicle from a simple idea, a concept, to a real, globally compliant car, and we're starting completely from scratch. This is the question. This is what keeps engineers like me up at night. Seriously, we're not talking about building a toy here. We're talking about delivering real automotive-grade safety and reliability, but under absolutely crushing cost constraints. This is where the real engineering, the real challenge begins. And this slide right here, it just lays bare the fundamental problem. Yeah, the sticker price might be a tiny fraction of a standard car, but the engineering complexity, it doesn't shrink nearly as much, not even close. You still need a robust battery management system. You still need a reliable motor controller. You still need functional safety systems. This isn't a game of simplification. It's a game of extreme intelligent compromise and integration. So here's our game plan for today. First, we're going to tackle the biggest headache, navigating the mess of global regulations. Then I'll walk you through our master plan, the V model. After that, we'll get our hands dirty with the core hardware. And finally, we'll talk about how we prove it all actually works, from a single line of code all the way to a car on a test track. Okay, first things first. In any automotive project, you have to understand the rules of the game. And for micro EVs, it's honestly like trying to play 4 different sports at the exact same time. This is where we define the absolute boundaries of what our vehicle can and, just as importantly, cannot be. And that brings us to a really key concept we use called the regulatory envelope. See, normal cars follow globally harmonized standards, which makes life easier. But micro EVs, oh no. They live in this wild west of fragmented, often contradictory rules. So our very first job as systems engineers is to map out this entire sandbox to see if we can even find a path through it all. And this table just shows you the problem perfectly. Take a look. Europe, with its L7E standard, says our car can go up to 90 kilometers per hour, and by the way, it needs ABS. But hop over to the US, and it's legally capped at a strict 40 kilometers per hour. And then you've got China, which demands that the car can sustain its top speed for 30 minutes straight. That's a massive thermal challenge. So the big question is, how on earth do you design one car platform for all 3? Well, here's our strategic answer. This is the big move. We target the European L7E standard as our engineering baseline. Now, why do we do that? Because it represents the most comprehensive superset of requirements. By engineering for the toughest rules, the L7E rules, we can then adapt the vehicle for other markets, like the US, mostly through software changes and maybe a few minor component swaps. It saves us from a hugely expensive, complete redesign for every region. All right, so with our regulatory targets locked in, we need a master plan, a roadmap. For that, we turn to the industry standard V model. I want you to think of it as our GPS for development. It guides us from that high-level idea all the way to a fully validated, production-ready vehicle, and it keeps us from getting lost along the way. The logic of the V model is it's beautifully simple. On the left side of the V, we go down. We decompose the big vehicle-level requirements into smaller subsystems, and then all the way down into individual components. Then, on the right side, we come back up. We build and test those individual components, we integrate them into subsystems, and finally, we validate the complete vehicle against those original goals we set. Let's just walk through a quick example. We start at the top with a requirement like, the vehicle's range must be over 120 kilometers. Okay, that requirement drives the system architecture, how the powertrain and battery talk to each other. That then dictates the detailed design of the motor and its control software. Then we flip to the right side of the V. We test that motor on a bench, we integrate it into the powertrain, and finally, we drive the whole car on a track to prove we hit that 120-kilometer target. See? Everything is connected, everything is traceable. Now, in a project like a micro EV, where every penny counts, this is our mantra: shift left. What it means is we do as much testing as we possibly can, as early as we can, using software simulations. This approach, called model-based design, lets us find and fix bugs in our control logic when it's just code, which costs basically nothing, long before we ever cut a single piece of metal, which, trust me, can cost a fortune. Okay, let's get into the hardware. The fun stuff. This is where we make the critical decisions that really define the vehicle's performance, its safety, and a huge chunk of its cost. We're talking about the electric heart of our machine. First big choice, battery chemistry. Now, you might see NMC cells used a lot because they offer more energy in a smaller package. But for us, for this application, lithium iron phosphate, or LFP, is the only strategic option. And the reason comes down to one word: safety. China's GB 38031 standard has an absolute red line called the 5-minute rule. It says if one cell has a thermal runaway, if it catches fire, the rest of the pack cannot go up in flames for at least 5 minutes. LFP's superior thermal stability is absolutely non-negotiable to pass that test. Next up, the drive unit. We specify what's called a 3-in-1 e-axle. This is just a smart way of integrating the motor, the gearbox, and the inverter all into one tidy housing. Now, this isn't just to make it look neat. It dramatically cuts down on weight, on complexity, and maybe most importantly, on the number of high-voltage connection points. Fewer connections means fewer potential points of failure, which directly boosts the system's reliability. All right, let's talk about a critical but totally invisible safety system, the high voltage interlock loop, or HVIL. It's a simple, low-voltage circuit that acts like a continuous safety check on every single high-voltage connection in the entire car. If any connector starts to come loose, even by a millimeter, this system is the very first to know. And the logic behind it is just foolproof. Look at the sequence here. When you plug in a connector, the long power pins touch first, but nothing happens. No power flows. It's only when the shorter HVIL pins connect that the vehicle's brain, the VCU, gets the all-clear signal to energize the system. And when you disconnect, the magic happens in reverse. The HVIL breaks first, instantly telling the VCU to kill the power in milliseconds, before the main power pins have even separated. It's an incredibly elegant, life-saving design. So all of these systems we've talked about, the battery, the e-axle, the safety interlocks, they're all orchestrated by this, the Vehicle Control Unit, or VCU. It really is the central nervous system of the car. It's what interprets your foot on the accelerator pedal, it manages energy to squeeze out every last bit of range, and it acts as a translator between all the different components. It's the conductor of the entire orchestra. A good design is just a theory. A great simulation is, well, it's just a really good guess. Now we have to prove that all of this actually works in the real world. This is the verification phase, and it's where we move from the virtual world of code to the physical world of the road. Our testing follows a really clear progression, a gauntlet, if you will. First, we test the brains, the actual VCU controller, on a simulator in what's called a hardware-in-the-loop setup. Once that passes, we test the muscles, the entire powertrain, on a rig called a dynamometer. And it's only when that's validated that we finally test the whole athlete, the complete vehicle, out on a real proving ground. So how do we keep track of all this testing? With the single most important document in this entire phase, the Design Verification Plan and Report, or DVP&R. This is our master checklist. It's our Bible. It links every single requirement from our original plan to a specific test, a specific method, and a very clear pass or fail result. Let me tell you, in automotive engineering, if it's not in the DVP&R, it might as well not exist. And this slide just shows its power in action. Remember that super tough Chinese requirement for 30 minutes at max speed? Well, here it is. The DVP&R says it will be tested on a proven ground, and the acceptance criteria are crystal clear. No overheating alarms, and the speed cannot decay. Same for that HVIL safety system we talked about. The test method? A bench test. The acceptance criteria? The VCU has to cut power within 50 milliseconds. It's this level of rigor that ensures safety and quality. So, to wrap it all up, this really is the core philosophy. Success in this hyper-competitive space doesn't come from some revolutionary new physics or some magic new technology. No. It comes from mastering how all the existing, proven systems can be perfectly integrated and balanced within an incredibly tight set of constraints: cost, weight, and regulation. And that kind of leaves us with a final thought to chew on. As the entire automotive world shifts towards more efficient, software-defined vehicles, you have to wonder, is this disciplined, systems-first engineering approach, an approach that was really honed in the crucible of the micro-EV, is this actually the blueprint for how all future cars will be made? It's something to think about.